Okay, so I wanted to go through the coil collapse transition. So if you look at uh, the states that the polymer chain can be in, the Gaussian states, the normal state, and then the random walk state, and then if you put it into a good solvent, you get an expanded coil. And if you charge the chain, you get a polyelectrolyte, would be the rigid linear structure. And if you go to porous solvent conditions, you get this collapse state possible if you're within the region where you're dilute. So if you're in this region of the phase diagram, you're in dilute, you're below C star, so you have independent coils, and you drop the temperature below the phase separation point for this point, because you can't dilute the chain anymore here. So if you're good solvent up here, and you have a region where you have a theta condition, then you collapse the coil into this region and make a 3D structure from it. And so the question is, like, how does that happen? That doesn't happen in a discrete step. It happens over a range. And so you have expanded coil, and it gradually collapses into the theta, then it gradually collapses to the collapsed coil. And so this isn't a step change, it's a gradual transition. So the question is how that happens. Right? Um, so we had for the short range interactions this characteristic ratio, C infinity for infinite molecular weight characteristic ratio at the plateau of the Kuhn length. Right, so C infinity would be like LK over the chemical unit of the chain. It's kind of a measure of the stiffness of the local chain. So Flory, to describe long range, that's short range interactions. To describe long range interactions, he came up with this coil expansion factor alpha, which has the same form. It's R squared over the theta condition chain. So you have the expanded coil over the theta. In this case, this is the chemical unit in L squared, and this is the actual chain in NK LK squared. Right, so they look the same, but they mean different things. Like the R naught here is for a chemical unit in L squared, and R naught here is for a theta condition chain, like a real chain at the theta condition, theta temperature. And this is the expanded coil at a higher temperature. So he didn't originally intend to describe collapse coils with this, but basically the same alpha is used for that. So that was in the early 67 or something, I think. And then de Gennes came up with this idea that you could redefine this alpha squared instead of alpha. So in our expanded coil situation, this alpha goes to n to the 1/5 power, and then this alpha would be to the 1/10 because it's the square root of this alpha. Right. So there's a difference in nomenclature, even though it's the same. So I'm following this Grossberg book. This guy. I'm following this Grossberg book, which is linked up on the web page, and then page 167 is where this stuff is somewhere here. 67, 64, 567. So this is like the coil globule transition. He goes through it. This book doesn't have the equations exactly, like it's missing equal signs and things and pluses. So it's a little bit messed up, but basically I think you can follow it if you follow the notes. If you want to read, Anyway, so the idea is you're going to use the same alpha for the collapse transition. Then how would you rewrite the so here's the alpha's into the 1/10 for using this definition of alpha, and that's 1/5 if you use the Flory definition. So how do you change the equation? This is actual simulation of like an expanded coil, so it's much larger than the Gaussian. That's a Gaussian chain, and the collapsed is a size transition to the collapsed. So this is a 3D object, this is a 2D object, and this is a 3/5 or 5/3 D object, 1.67 fractal dimension. So there's quite a bit of difference in size for the same molecular weight, these three. So nice. And then if you look in a melt state, this is kind of a picture of what a globule would look like this. In other words, if you took this structure, then you made the chain rainbow. So in other words, you're going down the rainbow as you go along the contour length of the chain. So basically, the different colors are all mixed randomly. That's the idea of this. And that means that the chain segments aren't located near each other in terms of contour distance apart. They're far apart. So it doesn't know it's the same chain. It's kind of a tangled up yarn ball that basically you can't tell that two pieces of the yarn are the same yarn or different yarn. Anyway, so this is used, this kind of collapse transition, a guy named Tanaka at MIT kind of made a big splash with this idea that you could, through a thermal transition, so this is a temperature-driven transition, if you make a network out of this, so you make a gel in water and then you change the temperature and it'll collapse down. So this is kind of a mechanism to make like an artificial machine or something, or artificial muscle or drug delivery. So as it shrinks down, you expel the drug. So he's saying like the control of this could be like temperature. You can also have a chemically driven collapse like that. So we'll see in the homework, it's driven by just the presence of other molecules near it can drive this transition. So just putting in ions or put in proteins or some other molecule next to like DNA or RNA, you can force this transition to happen. So there's kind of biochemical or ions can drive it. And then some people have looked at electric field light. If you put the right molecules into it, you can drive the transition that way. Right. So there's different ways to kind of control. If you make a network of polymers and you want this kind of transition, it's possible to control it. But the theoretical understanding of that is kind of what we're looking at here. So anyway, so when we did the good solvent using the Flory-Krigbaum approach, they couldn't integrate R squared PR because the function was too complicated to do a numerical integration. So they are an analytic integration. So rather than doing the integral, they took the derivative and set the derivative to 0 to find the maximum probability of a chain of length distance R squared, right? And then by solving that equation, they got the 3/5 that the chain distance, end-to-end distance is going to follow 5/3 scaling and molecular and 3/5 in molecular weight. So it's a 1.67 fractal dimension object. Right. So Grossberg, so Grossberg is the one that worked out more or less this coil collapse thing. And the first step of that is to kind of rewrite that approach, right? So rather than talking about so rather than talking about R is the number that he's looking at, he rewrites it in terms of this alpha. So this alpha, the alpha that's his definition of alpha, which is like this alpha. So alpha is R over R naught being the R theta condition, and this is the expanded coil. That becomes a parameter that he's interested in, and he doesn't work about the probability. He writes the free energy of the chain, which is where we equated the two arguments, the exponentials for Boltzmann and for the coil, right? The Gaussian distribution and the Boltzmann, and you can get this free energy expression. So in the Boltzmann, it's minus free energy over KT, and you make that equal to the 3/2 R squared over NL squared term, like this term, right? And then later we add in another probability term, but that term can also add into the free energy, right? So you get, this is the excluded volume term, and this is the rand entropy term. So he's got this has a temperature dependence. So you have Ts, and this one doesn't, even though it's got a T here, but chi is 1 over T, just like just like van der Waals' second virial coefficient is A over T, right? So even though you have T in both terms, this T gets canceled by chi, which has a 1 over T. So it's a hardcore excluded volume that's entropic, and this enthalpic excluded volume. That's got to do with the attractive potential between the polymer and itself in the context of the solvent, right? So anyway, so this is the expression we had before, and then you're going to want it because when you get to, so this is under a condition where the chain segments are far apart, and when you bring the chain segments in closer together, you have to consider higher orders in the virial expansion. It's like, in other words, if rho is going to be, say rho's volume fraction, so it's going to be less than 1. So if it's much less than 1, then like 0.1 squared is 0.01, and then it would be 0.1, and that's much larger. You can ignore the third viral. But if it gets to be like 0.5 or 0.6, then all of a sudden this term becomes more and more important. The higher the concentration, when you go to the collapsed state, you're getting to a high, like a really high density of the chain in the collapsed state, right? So then you have to include at least the third viral coefficient, maybe more. But you can solve it. You can solve the whole thing if you use a third. So that's kind of as far as people go because it gets too complicated. Anyway, so you're gonna add in. So here you just have so B is the first viral coefficient. This 2 chi, or this is the second viral coefficient, 2 chi, and the first viral coefficient is a 1. And then the third viral coefficient you want to add into this thing. So that's kind of the idea of the coil collapse is going to add in the third viral coefficient. Then you get kind of a universal equation for the free energy that can describe both the Gaussian, the expanded, and the collapsed, because these terms drop out when you get to the different alphas. So alpha is going to be, if alpha equals 1, you're at Gaussian. If alpha is bigger than 1, then you're an expanded coil. And if alpha is less than 1, then you get a collapsed coil. So basically, so Grossberg first did this, what Flory did, but instead of taking the minimum of the R squared P of R, he's taken the maximum of the R squared P of R, which is the derivative equals 0. He found the minimum in the free energy, which is like the equilibrium point, right? So that's also the derivative of this equals 0. And if you solve that, you find out that alpha equals this expression. So this ends up being the same answer that we had before, that R goes with the molecular weight to the 3/5 power. So it's still a 1.67, so 5 by 3, the DF structure. And then you have this, just as we had before, the B is the argument here, the 1/5 power. It's the same expression that you get from the Flory approach, but this is an approach that you can use to add in the third viral coefficient to that expression, and then you can talk about the coil collapse transition with the same function. So, I showed you this before, that you can do the same thing with the van der Waals model. So you have the van der Waals equation, and you have binary interactions, and you can have ternary interactions with some other constant. So A would be the attractive potential between particles, and the C's kind of a repulsive potential that's associated with the third particle coming. So you have, this kind of shows like you have an attractive between two particles. That's A. That allows you to have phase separation because they'll attract and make a solid or liquid. And then you have the third one is also similar to this one that attracts these two, because it's pulling that way, it detracts from the total kind of pressure of the thing. So the third one's positive, this is negative. That's the bottom line. This is kind of a linear picture of how that could possibly be. So you can see whether this is positive or negative is a little bit of a coin toss, and explaining it is a little bit of just a back of the envelope argument, right? That could go either way. So basically that how it is that this is attractive, that's kind of repulsive, right? So you can make if you make this negative, this A, then you have a situation where this is positive and the pressure increases here. You're not phase separating, but you're phase enhancing, right? You're mixing, enhancing in that case. And kind of the same with C. If it goes negative, then it does the same thing that A does. It causes phase separation, right? So these things can have signs plus and minus. And when A is 0 without C, that's the critical point. And C is 0 means you don't have ternary interactions. So again, like this starts to get kind of complicated, right? When you even just adding one term, it starts to get like, what is this thing? Becomes a question that you can spend some time thinking about. I mean, the other thing is that, I mean, so for instance, there's another way to look at this whole thing, and that A is like a spherical interaction, and C would be if you had elliptical structures, so asymmetric. So C can also be an asymmetry number. And there's like a couple other ways to think about these, right? So it can be attractive repulsive, it can be binary, ternary, it can be cylindrical and elliptical. And then you could have another one that would be like whatever is beyond elliptical for shape, right? So these can be like shape factors too. And so there's different ways to look at this, the kind of the viral expansion thing. Anyway, so that said, so you can solve these, and I did this before, that you can say like B2 is B minus A by using this geometric series argument. You have a 1 over V minus B, it looks like that. Then you can get it to just be a power series. Just look at the first two and you end up with that expression. And you can kind of do the same thing and get the third viral expression being, just because it's rho squared, it's going to be volume squared. B is the excluded volume. And then C is going to have units of KT volume squared. So energy volume squared. This is energy. This is energy times volume, A. Right. So anyway, so that's kind of how this pans out. So with the van der Waals and the viral expansion, you can get an expression for B2, B3. All right. So all right. So, and again, like B2 positive means miscible and negative means immiscible. And B2 equals 0, that's a phase separation point if you're ignoring B3. Right. So you're kind of looking for this to go to 0 at the theta temperature, which is a critical point where the thing goes Gaussian, becomes an ideal chain. All right. So anyway, so you have that expression. So you can see this becomes like powers of alpha. So you have like the ideal is alpha squared. And then this excluded volume term is 1 over alpha cubed. Then the next one's going to be 1 over alpha 6 for the third viral coefficient. Right? So this is kind of basically the scheme of how this is going to look. Like you have the energy, then N would be like the density squared and the density cubed. And then that gives you this expression. Then you're going to, so I just said, C is always positive. What is it, theta, da, da, da. So there's another issue here. So this transition to the coil collapse, so it can be either a first order transition or it can be a second order transition. So here, this is in a synthetic polymer, it's polystyrene and cyclohexane, I think, polystyrene and cyclohexane. So here, as you cool it down, this gradually changes, right? It's continuous function, right? But that doesn't have to be the case. So it can be the case that you cool it down and then there's a step change, right? In that case, there's an enthalpy associated with that step change as a discrete volume change. So if you take the derivative of volume, so it's the thermal expansion coefficient, well, it's infinity when it's a step change. And here it's an actual value that changes through this transition. Right, so all these derivative terms have a discrete value, what's called a second order transition, and have a non-discrete value. They go to infinity if it's a first order transition, like a melting point. When you melt ice, there's a step change in the volume. The specific volume goes up. But so basically, there's a step change in the volume, a step change in the enthalpy, step change in the entropy, step change in the free energy. That's a first order transition in melting. If you take polystyrene through the glass transition temperature, there's just a gradual trend. So that's a second order transition. Like a glass transition would be second order. So there's no step enthalpy change. There's no heat of glass transition. There's a heat of melting, but not a heat of glass transition. So this process can be a first order or a second order transition. And one of the key, so if you have biological molecules like a protein or DNA or an RNA, when they fold, that looks a lot like crystallization. That looks like a first order transition. When you have polystyrene and cyclohexane, this looks like a second order transition. And the same equation should be able to describe both of those. Right, so that's a key element here is like how would you get an equation that could describe first order and second order transitions, right, out of this kind of scheme of zero coefficients. I mean, it looks kind of impossible to do, but it's done. Right, so the way it's done, first off, you say, so this is a construction. So the way these kind of thermal transitions happen is that locally, you get kind of a local collapse of the chain. So you're at the theta temperature, and then it's going to get smaller, right? So the chain itself, the chain's Gaussian when you reach this line. So right at that point, this is a Gaussian chain, NL squared. R squared's NL squared, right? So, and as you cool it down, so you're starting with the idea that it's Gaussian, and then something happens as you cool it down to make it smaller. And then once you get to this flat part, it's a 3D chain, right? So R n goes with R cubed. So R is n to the 1/3 power, right? So basically you get this 3D here, 2D here, and on the road it's 2D, 3D. So how do you get 2D, 3D? Well, you can get 2D, 3D if you locally have 3D. So you're gonna locally have the chain make a melt, little balls of a melt. And conceptually balls of a melt. I mean, you can't see the actual balls, but basically little balls of a melt. And the balls of the melt are connected in a Gaussian, so it's a 2D random walk. Okay, so, and as you cool it down more, the balls get larger, and then the thing eventually just becomes one big ball. If you heat it up, balls get smaller, and it becomes more, and finally a random walk. And so that's how you can get a continuous transition if you have this introduction of a new size scale in the structure. So if you do that, how many balls are there? There's G star balls, and G star goes with the molecular weight of the chain divided by the number of blobs or G star is the size of a ball. Z is how many units you have in the chain. Z divided by G star gives you the number of blobs. And then the number of blobs are Gaussian, so the coil size is R squared proportional to G times the size of a blob squared, right? So it's basically G star times some small r squared. Small r would be the size of the blob, which changes with the temperature, right? So the r squared can change with the temperature then. So G star and little r star squared change with everything changes with temperature with this scheme, right? Anyway, so locally it's 3D, globally it's 2D. And then that allows you to have 2 and 3D at the same time to have a continuous transition. So that's basically the idea, this blob concept, that you have a new size scale introduced to allow you to have a continuous change like that. So if you figure that out, if each of these blobs is thermally equilibrated, then it has KT energy. So you can say that the number of blobs is Z by the size of a blob. So KT times that gives you the entropy of the chain. And the size of the blob is going to be R squared NL squared. So basically you'll end up with this KT divided by alpha squared is the energy associated with this, what's called confinement. So the energy of the chain when it goes to this blob structure. And before in this equation, for the ideal case, we had alpha squared. So you have 1 over alpha squared and alpha squared, and you're going to sum those two entropic. So this is the entropic part of the chain, the random walk chain. You sum those two and you get alpha squared plus alpha minus 2. So when alpha is larger than 1, so when alpha equals 1, it's Gaussian. Alpha is larger than 1, it's expanded coil. Then this term drops out because 1 over something large is much smaller than something squared. And then when alpha gets smaller than 1, you have collapse. This term drops out gradually, and then this term takes over. So it allows you to have Gaussian expanded coil and collapse coil all in one equation, one entropic expression for one equation. So that's one change. You add that to the front end term, the ideal term. Then you have your so B's 1/2 minus chi. So or here it's 1 minus 2 chi because you have a 2 here. So B's the excluded volume. So V naught times 1 minus 2 chi. And then you add in your third viral coefficient, which has this basically the square of this term because you have rho here and rho squared here. So basically you end up with alpha 6 here, alpha 3, alpha 6. So what you do is you couple up all the constants in this thing. You just have the alpha dependencies. So you make it into this x for the B term and y for the C term. And then it's going to look like this. So you can simplify this expression into this expression if you just call the collection of the second real coefficient stuff into x and the collection of the third real coefficient stuff into y, and have this mess. And then if you say you're going to go to collapse, so alpha is really small, so you got smaller than the Gaussian state, then 1 over something small cubed is a big number, and something small to the fifth is a really small number, and something small is a small number. So you can forget about that part, just have this part, which simplifies everything. Then you get if you're trying to solve for alpha, which is proportional to r, you're going to end up with the cube root of this this x over y, and x is b, y is c. So you end up with a cube root of c by b for r. So this is describing the globule size in terms of the third viral coefficient, second viral coefficient, and the cube root of the molecular weight because it's a 3D object. So r cubed goes with z, means it's 3D. The power of r is a dimension. So that checks out. And then you have this metrics for the third viral and the second viral ratio. Right. So that kind of determines the behavior of this thing. So you can, once you have solved for this R term, you can plug it back in and get the free energy expression, this guy. And then you can plot the free energy. Well, you can plot the alpha as a function of x and y. So this is alpha, the coil expansion. So below 1, it's collapsing. Above 1, it's expanding. And then x is the second viral coefficient. And each of these curves is for a different third viral coefficient. So x depends on temperature, and the third viral coefficient is defining like what kind of transition you have. So this kind of behavior where you have a continuous and you have a kind of a squiggly thing. So for one fixed value of temperature, which is x, you're going to have, say, the black line is a certain y. You have a value here, you have a value in the middle, and you have another value here for alpha. I mean, you have an alpha would be like an expanded coil or close to Gaussian coil, and then a totally collapsed coil in equilibrium with each other, right? So that was seen before in this Maxwell construction, which you may have heard of. So if you take the van der Waals equation, it's a cubic equation of state, and then cubic equation of state will have 3 roots within a certain region. That's the region where you have compatibility between like liquid and vapor, right? And that would be like the vapor liquid equilibrium point for a first order transition. See, they don't show that here, but they show it over here. So this kind of thing. That's Van der Waals' house somewhere in Leiden, the Netherlands, a place. Right? So it's got Van der Waals' equation written on the wall. I guess he did that when in his sleep or something. But anyway, so this is the PV for the Van der Waals equation, showing that in a certain region you have like 3 roots. If you draw a certain pressure, you have 3 volumes. The middle one's imaginary. High volumes like vapor, and the low volume is liquid. So you have liquid vapor equilibria. From that pressure, that volume, you can plot pressure volume and have the phase diagram. You have a critical point. The critical point will be here. Then the 2-phase region, the lower temperature, and then a single phase region up here. Right. So in our case, this is This region is a discrete transition for protein folding and for RNA folding and DNA folding. And then this region up here is a first order transition where it's a continuous transition without a discrete step. So here there's an enthalpy and you boil it and it goes to the liquid, or take the liquid and boil it, it goes to the vapor. So the more heat you put in, if you're at that specific volume, then you're gonna or if you're at that temperature, the heat you put in isn't gonna change the temperature, it just changes it from liquid to vapor. So the enthalpy of the vaporization consumes the heat that you put in. But when you're over here, you get a continuous transition, right? So this is second order, that's first order. That's basically the idea here. So you could get from this same equation, you could get polymer behavior or you could get biomolecule behavior, right? So that's basically the theme of this. Anyway, so people have kind of used this approach to so second order at the top, first order at the bottom. So this is studying this PIN-PM is a polyinosopropyl acrylamide. Phase separates at around 60 degrees centigrade. So in water. So you put this in water. If you cool, so it's a LCST, so phase separates on cooling. So hopefully I'll show you that on Monday. This is an LCST system. So you can see that it's showing this kind of, this would be a discrete transition behavior, right? So basically it's a step change between this is the coil size. So step change between the expanded coil and the collapsed coil, right? By tweaking the chemical composition of the side group, you can make it go from first order transition to second order transition. This paper in says 2008 or something. Right? So they showed that you could do this with by just changing the chemistry of the. So this is meant as like a model of how you could have a synthetic polymer and then a like a bio polymer kind of behavior. What they did was they did dynamic light scattering to get the hydrodynamic radius. They did light scattering to get the radius of gyration. And then if you have structures that are 3D, so this number will go to 0.774 for a 3D object. And if it's a Gaussian walk, so the ratio of radius gyration to hydrodynamic radius has different values depending on what structure it is. They have 1.5, that's a theta coil, 1.6 expanded coil, then it transitions over to draining sphere. Right, so they see 3D and kind of 2D structures, and they have a discrete, like enthalpically driven transition going on. That was a first order transition. So that's kind of the picture of this. These molecules have this amine group and a carbonyl group. So this is negative bias, and this is kind of positive bias. So these things can kind of couple together. So things that have this kind of grouping in it, like nylon, it's got a carbonyl and a amine, right? So this is plus minus. So these things will like hook up with each other, like the O's go with the H. So you can line up these chains together and make a sheet structure, or you can make a helical structure in nylon. And a protein is the same kind of setup. So it's got an amine and a carbonyl. And then again, like this double bond on the carbonyl can flip it over here. And that means these things are all planar. So it's conjugated through this bond. That makes this whole unit planar. So that's kind of like a card. And then this alpha carbon will have the functional group on it for a protein. So that's an amino acid. They have a mixture of different amino acids, makes a protein. Right. And then because they have a negative plus, these things will line up in sheets usually. Like the amine will hook with the carbonyl, and then they'll just line one on top of each other in a sheet structure, because it's already got like a sheet rigid structure to it and a planar setup. This kind of conjugation on the bonds. Anyway, so nylon's almost like a synthetic protein in a sense. You know, it looks, except instead of having an alpha carbon, it's got like some kind of alkane this would be nylon 6 as a butane linkage in the middle. Whereas a protein just has one carbon with some functional group sticking off. Right. So this stuff looks like that, except the main chain is a alkane, and then it's got the kind of protein group sticking off the side. So it does the same kind of bonding, hydrogen bonding, bonds with water and also bonds together. So this kind of interesting ionic things going on with that. So this penny PM is like a popular item for drug delivery. Anything where you want to see a transition, like Tanaka's gels back here are made from that same material. Tanaka's MIT stuff was all done with basically penny PM. These are all penny PM gels. So that's about it for this thing. Let's see. 1019. So yeah, I'm a little bit earlier on this, but hopefully that's okay. So I can kind of look at the let's see, out of this. What I can do is I can just glance at the homework a little bit here. Oh, if I can find it. So I put up the homework. It says like next week, post it early. So this is so there's 3 papers here. Let's see, let me go back. Right here. So I got this guy. This hot paper is the better paper. That's why I'm doing that. And then this thing, and this is Grossberg's book. If you want to get the Grossberg book at this point, you have to put an F here to kind of get that. So that's his book, and it's page 167 is where I wrote it here. 167 is where that coil collapse stuff is. Anyway, the Ha thing. So this Ha thing is kind of the first of the series of papers. So he's looking at the same thing, coil collapse, but he's saying like you have, so you can drive a coil collapse by adding in small molecular species. So you have this is RNA, some RNA molecule, and you add in like protein or some other kind of molecule around it. What happens is that when you have, so there's, let's see, I can go to that thing here. That's why I have this. So if you have, let's see, how much time? We got a couple minutes, so I'll just go through this. So if you have, say you have a solution with polymer in it, right? Say you're at a much larger scale, so you can't see that each of these things is a polymer chain. And then I could make a membrane here, right, that didn't allow polymer to go through. So you have just one side like that, right? So the liquid, and you have liquid on both sides. So the liquid here wants to go over here to dilute that, to dilute the polymer, because it wants to have an equal concentration on both sides. It can't bring the polymer over here, so it tries to dilute it. So it'll push this liquid up, right, to a higher light level like that. Right? That's called osmosis. And the difference in height here is like rho GH is going to be like PV. So you get a pressure increase. So there's a pressure increase on that side versus this side. This side's P, this side's P plus this extra pressure called the osmotic pressure. Right. So basically you can think about, another way to look at this is you can think about each of these little polymer chains as having like KT energy flying around. Then this becomes just like a gas. So these little colloidal particles are acting like a gas, and they have a pressure pi. So they have an osmotic pressure pi. So there's an atmospheric pressure, and there's this other pressure pi that has to do with, if you consider, you could ignore the water and just have the polymer things floating around with KT, they would have that pressure. Right. So if you take two plates, and then you have rather large polymers, and they can't fit in there. They can't fit in the hole. Then you get this same kind of osmotic pressure, it kind of pulls the liquid in here wants to flow out to dilute the polymer. So it pulls these plates together. It squishes it. So there's a force that's created, osmotic force associated with osmotic pressure that drives that thing shut. That's the idea. So if you have a case where you have DNA or RNA, and then the spheres here, because it's excluded volume, there's a region where these kind of extra molecules you put around can't get to because there's an excluded volume around it. So in that case, there's a pressure that's created, especially when there's an overlap of the excluded volume. So this is basically like our two plates. And at that point, that creates a vacuum here. That makes the thing collapse. So you can, if you change the concentration of the little gray things, so phi C would be the what's it called? The gray things. So the concentration of the gray things, you can go from R0 expanded coil, and you can add in enough that it'll make it collapse. That vacuum will make the whole thing collapse. Right? And that can be just a very discrete, like a first order transition. So this is the idea for if you're looking at this would be in a E. coli chromosome, and like looking at how the other materials that are inside, there's RNA and there's other materials inside, and how the other materials inside would make that thing fold, make the RNA fold into a small, from a millimeter size to a micron. Basically 3 orders of magnitude shrinkage in size when it folds. I mean, there's more to it than that, but basically this is one of the schemes, and they're using exactly the same equations, except they're adding in this kind of potential between the you see somewhere here you end up with the same equation. Like, and there's 3 papers here, but so it's the same alpha somewhere here. Here, alpha squared and alpha cubed, alpha 6. So this is like second viral B. So nu is the second viral coefficient, and this is like the third viral coefficient. And this is our entropic mixing term. So it's, and they end up with the same kind of Flory alpha 5, alpha 3 thing that gave us the 3/5 power. And so anyway, it's the same kind of stuff. It's a little bit twist on this coil collapse thing. There's 3 papers. This one's 2024, and then he references this Ha paper, and he also references this paper by Kang that's studying the same system. So that's more or less what the homework is about. So I guess that's about all I have for this. So I'm going to quit here. So it's about 10 minutes short, I guess, but I think it should be good enough. Then on Friday, I'll go through those papers and the homework, and then hopefully that'll be okay. I guess you can email me questions if you want, but basically I'm going to be traveling the whole time, I think. Like I have to go to Switzerland and kind of come back, and it's a day of just like total meetings. So it's kind of question. I'm not sure how much email I can answer, but I can answer stuff on Friday, hopefully. So anyway, so sorry I'm not here. Hopefully this will be okay. All right, bye.